Hello, everyone. Welcome to lecture week 11 of Quantitative Trading Strategies. So we're going to touch upon a slightly more advanced topic, which is on optimization. And in this video, we're going to consider treating the trading strategies as an optimization problem and look at how to optimize the specific trading strategy. So we know that different testing periods likely exhibits different characteristics in terms of the asset price curves, right? Means their profile is different according to the horizon, different time periods. So in order to be able to say that I have a solid, robust trading strategy, that we need to have to run the backtest over multiple periods or over test periods for a specific set of parameters. And this test periods needs to cover the representative scenarios, right? So what if the market crash? What if different scenarios happens, right? So the small probability events. So that's so if a set of parameters survive, right? So they still prove profitable, right? And over multiple backtesting periods, that means that they are robust and they probably will do well, and hopefully will do well in the live test. So live test means we put it in live for some period of time. However, so if we do this manually, right, we manually fine tune the trading strategy by changing the different parameter configurations, then this will become a very time-consuming process, right? So there are different reasons because the number of possible parameter values to test out may simply be too large. For example, in the previous lecture, we talked about the entry and exit signals, the thresholds we use to generate the trading signals. Now, for example, the entry signal, we set it to 2, which stands for 2 standard deviation, but now it could be 1.9, 1.91, 1.911, right? So it takes an infinite amount of values. We do not know which one is the optimal, right? So that's where optimization comes in. There's another aspect, which is that the backtesting for each period is not instantaneous. So each round of execution may take very long because we need to run for multiple periods, and each period may take some time to pop out results. And so this becomes a time-consuming process for single evaluation, right? And I want to know how a single parameter set parameters work, then this takes some time. So this further exacerbates the challenge in the so-called global search of the optimal strategy parameters. All right, so now we're going to view this as a so-called parametric trading strategies, means that this strategy is based on the certain parameters, and these parameters serve as the input variables. So we're going to have input variables. So typically a trading strategy has one or more parameters, and these are the so-called tuning knobs we're going to play around. And each of them will fall into a pre-specified range. So for example, for the intrinsic signal for the z-scores could be usually from 0 to all the way to 3 or even 4, right, or even 5. All right, so for example, for the trend following strategy, it relies on the 2 moving averages, right, the short window and long window. Now, we can have 2 parameters, which is the window size, right, of these 2 moving averages. So these are inputs, and our targets is can be put in the objective function. Right? So this is a function that takes the input of parameter values and output a metric, an objective. So in this case, we can choose the Sharpe ratio, right, as the performance measure, and over some backtesting period. So again, mathematically, we have 2 windows L1 and L2. Then we can represent the objective function using S, right? So S is a function, F of these 2 parameters. So here, something to notice that this F represents our so-called black box function. So this is black box because we do not know anything about the objective function, which is the Sharpe ratio. right? So we know how to calculate it, but we do not have a fixed mathematical form that we can use to derive its closed form solution. Right? So that's treating the strategy as a black box function, where we can use the tools in Bayesian optimization to find the global optimum in a shorter time. All right, so let's look at the optimization problem properly. So we have two window lengths, so L1 and L2. In the trend-following strategy, then this F is the black box function that takes the parameters input and returns the scalar performance metric. So it's just one number, a Sharpe ratio of a given training strategy. So our objective again is to find the set of parameters such as our Sharpe ratio is maximum, right? There may be some other constraints. In this case, the input parameters that are integer values, right? So these both needs to be integers. And we also need to satisfy that the short window needs to be less than the long window. Right? And also, we do not have the explicit functional form or gradient information of the function itself. Remember that when there's an explicit form, that makes it much easier to do mathematical analysis. But in this case, we do not have any information about the form of the black box function. And again, our goal is to figure out the set of input parameters that achieve the higher Sharpe ratio. So by the way, the gradients information is important because usually in machine learning, we use gradients, especially in deep neural networks, we use gradients to do optimization. But now since gradient is not available, then we cannot use the gradients descent algorithm. So this is the overall process of viewing the training strategy as an optimization problem. Specifically, this falls into the global optimization scheme, right? So where our goal is to locate the optimal set of parameters of interest, right? And our search space is over the whole search domain, and we need to be careful about the limited resource because we cannot randomly evaluate. So our search needs to be intelligent and needs to be principled, right? So our goal is to try to locate the global maximum F star. So this is our global maximum. This is our final destination. We'll also find the corresponding location X star, which is representing the input parameters. So mathematically, the F star is defined as the maximum of all the functional values of the Sharpe ratios. So this is the highest Sharpe ratio. Or we can say after we find the optimum parameters, we just do one evaluation to calculate the Sharpe ratio. That Sharpe ratio is the highest. Right? So this is two equivalent forms. We can also just say what interest in the location. So X star is defined as the argmax. So this is define the argument that maximizes the function itself, right? Which is the governing the calculation of the Sharpe ratio. Global optimization can be very difficult because this is one example of a function curve, right? So we have the x on the x-axis and we have the f. So this is our targets. This is the global maximum. Defined this in this way, so maximum of all the values. And this is our total search space, so the domain of the function, right? Domain of the function. So our goal is, for example, say starting from here, how do we land in at this point, right? So this is a global optimization problem. All right, so that's it for this video, and thanks for watching. I hope to see you in the next video.